All right, welcome to our lesson on current electricity. And so today what's going to happen is we're going to review some of the stuff that you would have watched on Friday. And I'm going to specifically point out some of the things that you need to know and how we are going to use them in this course. So it's hopefully Monday, January 10th, when you're doing this. And so we're going to just talk about current first. So current, which has the symbol I in a circuit, is the flow of the electrons. In a circuit. Now, for a long time, when we were just discovering electricity, and by we I mean scientists, they thought that the positive charges were flowing. But now we know that it's the negative charges that are flowing, and so, yeah, the electrons are what are moving. And the reason for that is just because of where the electrons are located, right? They're located in the rings around the nucleus. They can be taken off of the outer shell so that they can flow through. And copper, in particular, has 29 electrons, but it only has one on its valence shell, which is the fourth shell, and it makes that one very easy to take off with a little bit of force. And so good conductors of electricity are actually the same as good conductors of heat. They have these free electrons that are coming out of the valence shell. Good insulators, as far as electricity is going, have bonded electrons. And so the electrons can't move through very well. So good conductors, things like metals, especially, but also water can conduct electricity, but only if it's not pure water. Pure water actually does not conduct electricity. So what's conducting the electricity is actually ions and particles that are dissolved in the water, and not the water itself. So when we're talking about flow, we use coulombs, which I always spell wrong, actually. C-O-U. I never remember which O to put the U with. So coulombs is a group of electrons, and the number of electrons in a coulomb is 6.25 times 10 to the power of 18 electrons, or 1 electron has a charge of 1.602 times 10 to the negative 19 coulombs. So coulombs is just a way of measuring charge, and so it's a group of electrons. So the flow of the charge in the conductors is called current. And so current is measured by doing Q over T. So current, which is measured in amps, named for Andre Ampere, is the amount of charge per time in seconds. We want time in seconds again, and that's normal. All through physics we've been doing our time in seconds. So to measure the current, it would be how many coulombs. So for example, 4 amps means 4 coulombs of charge pass in a circuit in 1 second. Okay, so 4 amps means 4 coulombs every second. We measure current using an ammeter. And so as part of this note as well, and hopefully this is also basically a review of grade 9, some of the things that you would have learned with electricity in grade 9. So to draw a battery, we draw a small line and a long line. The small line is the negative terminal of the battery, and the bigger line is the positive terminal of the battery. On the video, they called this a dry cell, and that's because it's dry. You can also have a liquid battery, which would be called a wet cell. An example of that is a car battery, where there's battery acid, which is a liquid inside of the battery as the chemical. But our batteries usually have a chemical paste inside of them, and so that's why they're called dry cells. So to draw an ammeter, we do an A in a circle, and it goes right into the circuit. I'm also on this circuit going to draw a light bulb, which is a loop in a circle. And I'm also going to add a switch, and in this case my switch is going to be closed. So this is a closed switch, which means that it's on. This would be an open switch, which would mean that it's off. And so I have my ammeter. So it is connected into the circuit to measure the current flowing through the wire. So the current that's flowing from the negative terminal of the battery, it's going through the ammeter and then continuing through the rest of this circuit. So it's measuring the current flowing through the circuit. With current, there's two types of current. The first one is alternating, AC, alternating current. And this is anything that's on a plug or an outlet or cord that is going to be running on alternating current. And what happens with this is that the electrons vibrate back and forth. The other type of current is direct current, and that's mainly what we're going to be working with this unit, which is anything that's operating on a battery, where the electrons only flow one way. So alternating current and direct current. And again, hopefully this is review from grade 9. The second thing to consider in our circuit is the potential difference. And when you see potential difference or electric potential or potential difference, that's the same thing as the voltage, which is the V. So the the energy equation for this is that we have chemical energy, which is in our battery, and it's stored up. It's a potential, right? Potential energy stored up, and it's being converted into electric, also potential energy. So the electrons in our circuit are carrying energy that could be used in our circuit. And so to calculate voltage, what we've got is the equation V equals E over Q. So this is the equation that was on our video. So voltage, which is in volts, also called electric potential, is the energy in joules per coulomb of charge. So joules per coulomb gives us the voltage. So if we have a 1.5 volt battery, it gives each coulomb 1.5 joules of energy to carry. Now, remember that a coulomb is in a big group of electrons, so each electron is not carrying that much, but each coulomb altogether is doing it. It is measured using a voltmeter, which is a V in a circle, but it's attached a little bit differently. So we're going to draw out another circuit here, and do give yourself maybe 7 or 8 lines to draw this out, because we're going to put some stuff around it. So here's our battery, and we're going to, in this case, we're going to draw a resistor in my circuit. So I have a battery and a resistor. So what is happening with the electrons, with the coulombs that are traveling around? When they get to the battery, they pick up 1.5 joules of energy, if this is a 1.5 volt battery, which we're assuming it is. So this is an electric potential gain at the source. So the battery, the cell in this case, is a source. And so as these electrons are going around the circuit, they are carrying these 1.5 joules of energy. When they get to the resistor, and when they have to go through the resistor, and resistance is the next thing that we're going to look at in our circuits, in our discussion on what's in a circuit, they lose 1.5 joules of the energy. So our resistor, which is that crinkly line there, uses the energy. And anything that uses energy in a circuit is called a load. So it uses up the energy in the circuit. Anything that takes the energy out. And so here what we've got is an electric potential loss. And so now they have 0 energy left, and they go back with 0 energy to the battery, and they pick up another 1.5 joules of energy. So that's how it works with an electric potential gain and an electric potential loss. So how do we connect our voltmeter? Well, our voltmeter is connected around our source or load. And I'm actually going to just redraw my circuit on the next page so that you can really see how to connect your voltmeter properly. So I'm just going to quickly redraw this. Notice I'm using fairly straight lines when we draw circuits. So the voltmeter, we would connect like this. We would connect it with wires before and after the battery, because, so it's connected around to measure the difference from one point to another. So here, remember we said they have 0, and here they have 1.5. So it's going to actually measure the difference between those 2 points. Or if we were measuring the voltage at the load, then we would connect it on either side of our resistor like that. So it's connected around to measure the difference, gain or loss. So what happens if there is no load? So if we have a short circuit, that means that there's no load to remove the energy. And electricity is lazy. It wants to take the path of least resistance. So let's say we had a circuit with our resistor, but somehow a wire got connected like this. So the electricity, instead of going to the resistor, it's just going right back to the battery. Well, what's going to happen is it's going to overheat, might explode the battery, might cause an electrical fire. Because think about what's happening. So we've said that as they come around, they pick up 1.5 joules of energy per coulomb, or 1.5 volts. And electricity is lazy, so it's going to take the easy way and go back to the battery. But now it's not at 0, it's at 1.5. And then it picks up more, and then it goes around, and it picks up more, now it's at 4.5, and it goes around, and it picks up more, now it's at 6, and it goes around, it picks up more, now it's at 7.5. And so what's going to actually happen is it's just going to gain energy and gain energy and gain energy, and it's never going to lose the energy over here. And so that is going to cause, overheating, especially with a battery. If a short circuit were to happen in your home, where there's alternating current, it might cause sparking and also cause an electrical fire again. So there's a couple of things we can do to help. We can use either a fuse or a breaker. And so a fuse looks like this, or a breaker. There's no dot there. So it's just two dots with a squiggly line in between. And a fuse or a breaker are designed to shut off if the flow of the electricity or the power gets to be too much. Now, the difference between a fuse and a breaker is that a fuse is a little device that needs to be replaced. So a fuse has a wire inside of it, and if it gets overloaded, then it's just going to shut down. It's going to break that little wire, kind of like an old light bulb would break and then it wouldn't work anymore. So a fuse, it's a little glass tube that needs to be replaced, and a breaker, like what you have in your home, is just a switch. So it just switches off and then you can turn it back on. So fuses need to be replaced and breakers just need to be switched back on. All right, to continue our discussion on parts of a circuit and things that are involved in a simple circuit, we are going to talk about resistance. So I just have a little meme here to show you. So ohms is what resistance is measured in, and so ohms make it harder for the energy or the voltage to push the current through the circuit. So this is the part where it takes the energy of the circuit to actually push the electrons through the circuit. So resistance is what makes it harder for the current to flow, basically. So that's just something I saw a while ago, and I thought, oh, it's kind of fun. All right, so when the electrons are carrying the energy, they need to use up the energy to pass through a resistor. And I just have a few resistors here to show you. So here are a couple of resistors that are different sizes and also different colors. There's a way to tell what the colors mean on each resistor, but these are two resistors, and they're made of like a ceramic material. This is another one. So this one is a 10 ohm resistor. It's just, it kind of feels like a coffee mug material almost, but a little bit rougher. We also have these white ones that we have. This is a 47 ohm resistor. So there's all different looks. These ones at the top here are ones that you would find in a circuit board. These bottom ones are just more designed for experiments and things like that. So resistance is measured in ohms, like I said. And the symbol for ohms is the omega sign. And how do we calculate it? Well, we use what's called Ohm's law. This was a guy named George Ohms who came up with Ohm's law. And Ohm's law relates the three major parts of our circuit. So R equals V over I. So resistance, which is in ohms, is equal to voltage over current. So volts over amps for your units. And what we can do is we can graph it. And this is what we're going to be looking at tomorrow, is calculating Ohm's law. Sorry, that's a bit blurry. There you go. So if you graph voltage and current, so potential different voltage in volts, current in amps, what you hopefully will get is something that's like a straight line. It's a linear relationship. So as the number of volts increases, then the number of amps increases, and the slope of this line gives you the resistance. So when you do volts over amps, rise over run, then you get resistance, and it's linear. If something did not follow Ohm's law, then it might curve up where the voltage increase, or it also might go like this, where the current change. But if it's linear, and hopefully with a resistor it should be linear, then it does follow Ohm's law. What affects the resistance? Or how do we make a resistor? The first thing and the main thing is the material. So these little resistors that I showed you, the material that they're made out of is actually what gives them the resistance that they have. Because this one, which is sort of smaller, is designed to be a 47 ohm resistor. And this one, even though it's longer, because of the material, it's actually only a 10 ohm resistor, so very small. So the material makes the resistance. For these next three, I want you to just think about trying to get down the hallway. as a person. So you are trying to get to your locker down the hallway. So think about this. If every other person in the hallway is moving fairly slowly, it would be easy to get around them. But when things get heated up, their particles start moving faster. And so imagine everybody around you in the hallway bouncing around very quickly. Well, you might collide with people a lot more often. And so it would make it harder for you to reach your locker. And so as the temperature goes up, the resistance also goes up. So it's harder for the current to get through. The next one to think about is diameter. So the hallway is a certain width, and if your hallway got wider, it would be easier to get to your locker because you would have more space to walk through. But if we made the hallway half as wide as what it is now, and everybody was still in it, that would make it a lot harder for you to get through the hallway. So as the diameter goes down, as it gets smaller, then the resistance is going to go up. And the last one to think about is just the length. And in this case, sort of think about the amount of energy that it would take you to get from the start of the hallway to your locker. Well, if your locker is halfway down the hallway, or if your locker is all the way down the hallway, it's going to take more energy to get all the way down the hall, no matter what the other conditions are. If the conditions were the same, it would take more energy to go all the way down the hall than it would to only go halfway down the hall. So as the length of the resistor goes up, then the resistance is also going to go up. So those are the different factors that affect the resistance. And those are the three things that we want to look at in our circuits: voltage, current, and resistance. You are going to have some questions to work on from here about all of these different things. And then tomorrow there'll be a lab on Ohm's law.